right, so what we're looking at today is we're actually looking at normal and continuous distributions. This is the third part of the exam review, and this is essentially Chapter 6. What it's talking about is, or what we are talking about now is we're moving from the discrete distributions, which we saw in Chapter 4, and we're now moving into distributions where what we're doing is instead of counting the random variable, we're now measuring the random variable, okay? And that's what makes something continuous, is that it's rather than being countable, it's what we call measurable, all right? And so for the purpose of this exam, there are just a certain set of skills that you need to be able to do. They're going to end up being very important inside of the next sections. So I want to make sure that you can do them, and that's why we're actually going to be giving you an exam on them. So let's take a look at one of the questions from the review. And let's use that in order to kind of like demonstrate some of the many skills that we have, or that you'll need to know. This one actually is, I believe it's question number 11. All right, and this isn't all the questions, and it's kind of got some other pieces in it in order to help me demonstrate some things about the normal distribution. But you can use this in order to do this set of problems. So let's first look, and we've got the high temperature in Chicago for a month of August is approximately normally distributed with a mean, mu, of 80 degrees Fahrenheit and sigma, standard deviation, 8 degrees Fahrenheit. Okay, so those are two very important pieces of information. And then the fact that the distribution is approximately normal is also going to be very important because it tells you what kind of distribution you're going to be looking at. That's actually a really important thing that's going to become even more important as we work in hypothesis tests and confidence intervals. Which distribution should you use? That's crucial. It's a crucial piece of information. So we now know that it's normal. And since we know that it's normal, we've got some information about it, and we have something that we know about the normal distribution called the empirical rule. Now, the empirical rule basically tells us, or more than basically tells us, it tells us how the normal distribution is divided up in terms of the amount of data in between certain amounts of standard deviations. So let's look at this distribution, right? So this distribution is for high temperature in August in Chicago. Okay, and so at the center of it, because it's normal, is going to be the mean, 80 degrees. Now, what we'll do is we're going to break this up. The empirical rule says break it up into 3 parts for each side. It's actually 6 parts, I suppose. All right. Okay, there we go. And since they're standard deviations, they should be approximately the same distance apart. Nobody's going to get out a ruler and measure, but, you know, they shouldn't be all over the place, okay? So basically mine are the same basic amount. Now, one standard deviation above the mean is going to be 88. What is that? That's 80, right, plus 8. A standard deviation plus 1 standard deviation. Then, next one, 96, that's going to be plus 2 standard deviations. And then 104, that's plus 3 standard deviations. That's hot for Chicago. It's not hot for LA, but it's hot for Chicago. So 80 degrees now, if we're going to go minus 1 standard deviation, we're now going to go to 72. Another one, 64. Now it's like, ooh, that's a cold August day. Okay, and then we have a really cold August day, which would be 56 degrees. That's minus 3 standard deviations. Okay, now, what this has done is that it's broken up this distribution into standard deviations, right? It's basically what we do is we called it, it's become somewhat standardized, okay? And since it's normal, we can now actually determine some things based upon the empirical rule. The first part of the empirical rule is that between -1 and 1 standard deviation, in this case between 72 and 88 degrees, right, in terms of high temperatures, we have 68% of the data. All right, then between -2 and 2 standard deviations away from the mean, we have 95% of the data. And then between 56 and 104, or -3 and 3 standard deviations, right? Just happens to be 56 and 104 for this one, because that's the mean and standard deviation for this particular distribution. In other cases, you're going to get different values, and that's going to be 99.7% of the data. Okay? Now, what we want to do now is we want to say, okay, well, all right, so I got 68%, 95%, 99.7%. what I'm going to do is I'm going to break down my distribution even more. So one thing I know about the normal is that it's symmetric. So if it's symmetric, that means that I've got 68% between -1 and 1. Just one of these things is going to be 34% of the data. So what we mean by 34% of the data, by the way, is the percent of days in August that have that temperature. That range of temperatures, actually, we should say. So 34% of the days in August are between 72 and 80 degrees. Well, symmetric, that means that it's also 34% of the days in August have high temperatures between 80 and 88. Okay, cool. Hey, that's not so bad. That's dividing by 2. Well, what about 64 to 72 and 88 to 96? Well, I'm going to do a little calculation. 95 minus 68, that's going to be 37. Now, 37 is how big both of these guys are together. So this one and this one put together are 37, right? Because they're like the extra amount. And so what I'm going to need to do is I'm going to take 37 divided by 2. That's 13.5. So 13.5% of the data on either one side of these guys. Okay. That's what that is. Then I'm going to say, okay, well, I'm going to kind of use the same idea. I'm going to take 99.7, and now I'm going to subtract out the middle two standard deviations. So that's 4.7, right? And we'll take 4.7, we'll divide it by 2, okay? And that's 2.35. So 2.35% of the data here, 2.35% of the data here, okay? And then finally, the question is like how much is out on here on the edges? Well, it's going to be 100, right? Minus 99.7, that's 0.3. And then we'll take that, divide that by 2, because we got the two sides there, and that's going to be 0.15. Okay. So inside of those little pieces, they're tiny. That's 0.15%, not even 1% of the data is in there. Okay, and that in those regions from 104 on. So in Chicago, if you ask, well, what percentage of the high temperatures are going to be more than 104? The answer is 0.15%. It's going to be really rare. On the other hand, if you asked, well, what percentage of the temperatures are going to be between 80 and 88 degrees? The answer is 34%. Or we might ask a question of, well, what percentage of the temperatures are going to be less than 88? Right, like strictly less than 88, well, that's going to be 50% for the 80 and below, and then plus the 34, so that'll be 84%. Okay, let's kind of see that, write it down a little bit. So we've got a question here. What is the middle 99.7% of the data? Oh, that's pretty straightforward. We saw that by the empirical rule, that's between -3 and 3 standard deviations, so that's 56 to 104. Okay, so that first one, that's going to be 56, and it's actually, 56 to 104 degrees. That's your middle 99.7. When we say middle, by the way, we mean symmetric on both sides. Okay? Middle 99.7, that's 56 to 104. What about the high temperatures between 64 and 88? Well, at 64, here's 64 right here. Okay? And here's 88 right here. So I'm going to take 13.5 plus 34 plus 34, and that's going to give me 81.5%. I hope you guys can see that. Actually, I'll highlight it. This grouping is going to look like this. So we want this group. All that. So all we got to do is just add up all that area. Add up all that area, right? Okay, so after we've generated the distribution using the empirical rule, we add them all up. Okay. What about what percent of the temperatures is less than 72 degrees? Well, now, that one is this grouping. There's less than 72. Okay. A couple of different ways we can do this, but probably the easiest way to go about doing it is we're just going to take 0.15 plus 2.35 right, plus 13.5, which equals 16%. There it is. And that's how you use the empirical rule when you have, by the way, this stuff right here, this is only, you use the empirical rule only when we have whole numbers of standard deviations. In just a second, we're going to see what we do when we don't have the whole numbers. And that's, if you remember, that's we're going to use the normal calculator when we don't have whole number standard deviations. If I ask you to use the empirical rule, you can bet you're going to be drawing me a picture of the distribution, calculating the number of standard deviations, and then telling me that number. If you go in and use the normal calculator for, say, for example, for these questions, the 64 to 88, if we actually are asked to use the empirical rule, then it will not be correct. I should let you know that again, that if it says use the empirical rule to find the 99.7% of the data, middle 99.7, you need to use the empirical rule. Okay? All right. Well, as kind of a corollary to the empirical rule, we have this whole idea of the standard deviation rule, right? What does it mean for a value to be unusual, like unusually warm or unusually cold? So again, remember that we have mu equals 80 and we have sigma equals 8. So a value is unusual if it is more than 2 standard deviations away from the mean. More than 2 standard deviations away from the mean. Okay? Now, what, maybe, and you know, deviations. Okay. Now, let's say, if I asked you the question, what temperature would be considered unusually warm? In order to show me your work, you're going to actually have to create like, you're going to have to show that it is in fact bigger than 2 standard deviations away from the mean. So maybe let's change this phrasing. Bigger than what temperature is considered unusually warm? All right, now all we need to do is we're going to take the value, call it x, is going to equal 80 plus 2 times 8, because that's 2 standard deviations above the mean. So that's 80 plus 16, which equals 96. So for this first one, it's going to be 96. It's going to be 2 standard deviations bigger than the mean. Okay? Right? 1 standard deviation is 8, 2 would be 16. What about what temperature would be considered unusually cold? Well, that one, call this x hot, x cold, is going to be 80 minus 2 standard deviations away from the mean. So 80 minus 16, which equals 64. And there it is. That one's simple. You just have to know, right, that to be unusually large, you're more than 2 standard deviations away from the mean. To be considered unusually cold, that means that you are less than 2 standard deviations away from the mean. You are minus 2 standard deviations, I should say. Okay, that's it. All right, now, finally our application problems. And these are different because what we're going to be doing is we're going to use the Z calculator, or the normal calculator on StatCrunch, or the normal calculator on your calculator in order to calculate these values. Okay, so let's say, for example, and I'm going to show you a very general way of going about doing this that pretty much it's going to make these a lot easier to figure out, right? It's systematic. It can be very quick if you practice it, and you will not make very many mistakes, okay? So let's first talk about z-scores. So a z-score is the number of standard deviations that a value is away from the mean. Okay? So, and how we calculate it is z will equal x, which is the value for the random variable, minus mu, the mean for the distribution, divided by sigma. And this is also called, you'll probably see it as a standard score, or a standardized score. And what that means is that what we've done is we've put it into numbers of standard deviations away from the mean, which allows us to use something like the empirical rule, or allows us to basically utilize that. It's essentially an integral, right? To solve for the probability of a particular event using the normal distribution. Okay? So, let's say, for example, I've got A. What is the z-score for a high temperature of 85 degrees? Well, z for 85, I'm going to write down the values that I need. I have x. X is going to equal 85, because that's the thing I'm looking for the z-score of. Mu, again, is going to equal 80. Sigma equals 8. So that's something that we already know. And then I'm just going to plug it into my z-score equation. Z equals 85 minus 80 divided by 8. When I calculate that out, that's 0.625. So what that tells me is that 85 is 0.625 standard deviations away from the mean. Not quite one standard deviation away from the mean, a little bit less. Okay? Not quite half less, but a little bit less. Okay? What about B? What is the probability that a randomly selected day in August has a temperature less than 78 degrees? Excuse me. Now, B, here's what I'm going to be expecting from you. Okay? So first, x is equal to 78. Okay? And I want to write a probability. Probability x is, what was it? Less than 78. Probability that x is less than 78. This is what I mean when I say something has probability notation. Right? I actually write the probability that x is less than a particular, whatever amount that I'm looking for. It's essentially going to be what you put into StatCrunch, but it is a way to communicate that that's what I'm looking for. Next up, so my answer is going to eventually be that, I need to find a z-score. I'll remind you of this, but you need to know that you do need to find a z-score. So I'm going to take 78 minus 80 divided by 8, and that'll end up equaling 0.25. Okay? Cool. So that's the next part. I've got my z-score. The reason why I want a z-score is because what I'm going to do is I'm now going to draw a distribution. The drawing of the distribution helps me to visualize graphically what it looks like to find this particular probability. At the middle is going to be my mean, 80 degrees, and then 78 is 0.25 standard deviations away from the mean, so I'm going to basically it's right there, okay? Right? It's not far away from 80. If I drew it over here, that'd be wrong. I don't want that. It's wrong. That's way too far away from 80, all right? Am I going to take out a ruler and figure it out? No, but if it doesn't look right, it's not going to be right, okay? So, next up, I'm going to shade, and since this is the less than value, I'm going to shade the less than side. I'm using color. You don't have to use color, but you are going to have to actually go in there, shade a properly drawn picture, right? And notice I did this. Now, StatCrunch gives me a picture, but I did this in order to help me visualize the problem, all right? So that I end up with exactly the right answer that I'm looking for. If you just go in and you use StatCrunch and then you draw the picture off of what StatCrunch says, you better be really confident that what you're doing is you're in fact finding the right value for that you've got your problem set up completely correctly, or else not only are you going to end up with like a wrong z-score, you're going to end up with a wrong probability, you're also going to end up with a wrong picture. Okay? And now that I've got that, now that I got the picture drawn in my distribution, now I'm going to just go into StatCrunch, go to Stat, go to Calculators, Normal, then my mean is going to be 80, my standard deviation will be 8, and I'm looking for the probability that x is less than or equal to 78, and I compute, and there it is. Ooh, I look at it, and so, oh, that looks really close to what I have drawn, isn't it? Right? So the probability there is 0.401. Lots of cool things go into, basically drawing this out, doing this particular way. Amongst them is the fact that I could tell clearly it's going to be less than 50%, just a little bit less. Yeah, actually looks like 10% less. And it allows me to kind of look at and eyeball my problem and say, okay, you know what? It looks kind of right. That looks like the correct answer right there. So you'll notice with these kind of problems, they're very systematic. I write down the values that I need for my problem, right? X is, in this case, 78. My mu and 80 and 8 are exactly the same. Then I write my probability notation. You'll notice that in StatCrunch, we use that probability notation right down here, right? Okay. So all I needed to do was just input it in once I wrote it. And then I find my z-score, right? Using my z-score formula, I draw my picture so that it looks kind of close to what it should look like, right? 0.25 standard deviations away from the mean. There it is. That's about 0.25. Got my mean at the middle. And then finally, I plug it into StatCrunch to get my 0.401, my actual probability. Okay? That's a complete normal probability application process. All right? I'm going to remind you on the test to go out and do that, but you should actually practice it on your reviews as well. Okay? All right, what about the next one? What is the probability that a temperature is between 80 and 83 for, not the same sample, but for this grouping, okay? Well, now, for C, I got X1 is 80 and X2 is 83. So in this case, I'm actually looking for a range of temperatures. It's continuous, so I can use the less than or the less than or equal to, but I'll just use the less than. And it should look, that's your probability notation, between 80 and 83, okay? And we'll eventually get an X equal to. I'm now going to find my z-score for 80, and that'll be 80 minus 80 over 8. We'll do the math, that's going to be 0. Then I'll find my z-score for 83, that's going to be 83 minus 80 divided by 8, and that equals 0.375. Then I'm going to go in, I'm going to draw my distribution. There's 80. My mean is 80, mu. And then 83 is 0.375, so it's a little bit farther off than where we had 78, right? Okay, so there's 83. And I'm going to go in here, I'll shade it. You don't have to shade in color. You just need to use your pencil in order to shade it. There's my shading. Okay. Now, when I go in and I actually calculate what this should be, it should be somewhere around there. I use my between calculator because this is a between value. This is going to be 3. Compute, and it's 0.146. There you go. So there it is, 146. Oh, that's about 146. All right, okay. Now, this last one is a little bit different because what it's asking us for is it's asking us for the values that will separate this portion of the normal out, the lower 80 from the upper 20% of temperatures. So when I'm looking for something like that, it's going to be a little bit different. Actually, it's going to be a lot different. So for D here, in this case D, what I'm gonna do is I'm gonna draw a picture of this one. I can't find a z-score because I don't actually know what values I'm looking for. I'm looking for the values, I'm not looking for probabilities. So I'm gonna put my 80 at the middle, okay? And what I wanna do is I wanna say, okay, well, 80 versus 20, well, 80%, right? Probably right about there, that's 80% of the data. So what I'm looking for is, I'm looking for whatever this x is. What is x right here going to equal? Okay. Over here on this side, this is 0.8. That's 80%. Over here on this side, that's going to be 20%, 0.2, and that's good enough. That's a picture that you need for this kind of problem. Now, conceptually, what we want to get is that what we're looking for here is a value for the random variable, and that we already know how much of the data is less than that random variable, okay? What we're essentially looking for is the probability that x is less than or equal to, and I don't know what that value is, and that's equal to 0.8, okay? And the reason why I set it up like this is because that's what we're going to do instead of stack crunch. Okay, I'm going to go standard. 80 and 8, still my standard deviation, my mean. Now x less than or equal to, and this is the thing, I don't know what that value is. But that's okay. What I do know is that this is 0.8. And I go in and compute. And that's 86.733. So, when I go in here, this is 86.733. This is 86.733. And what that's saying is 80% of the high temperatures are less than 86.733, okay, in August. So the difference here, and I want you to notice something about the questions, right? So in this case, it's asking for a probability. In this case, a probability, right? Okay. In that case, what you're looking for is you're looking for the area under the curve that's between, say, for example, 80 and 83, or that's less than 78. Now, in this case for D, they're looking for a temperature. What temperature divides the lower 80% for the upper 20% of temperatures? So you're given a probability, the probability of 0.8, and what you're looking for is the temperature. So you want to catch the difference in those questions. So as you're working through the questions, you want to kind of like recognize, oh, that's a difference in the questions, okay? And so that should kind of help you to determine when you're going to utilize the process that we use for B and C versus the process that we use for D, okay? When it comes to the normal distribution, it's what we want to get is there's a couple of things that we need to do. You need to be able to use the empirical rule to tell me what percentage of the data is between certain values when the standard deviations are whole numbers, when you have 1 or 2 or 3 standard deviations, okay, or -1, -2, -3 standard deviations. You also want to be able to tell what are the cutoffs for unusually high and unusually low, and how do you determine if a value is unusually high or a value is unusually low. And so basically all you need to do is show that in fact that value is more than 2 standard deviations away from the mean. And then finally, with applications, we either are going to be we need to be able to find z-scores, we need to be able to draw pictures of the distribution, and we need to be able to find probabilities of temperature ranges, or we need to find values of the random variable when we are given, percentages, right? So that's everything that you need to know in terms of the normal distribution. Okay, I hope this helps.